Hello everyone. Today we are going to study non-conservative force and potential energy. We know that forces are either conservative or non-conservative. Conservative forces were discussed in last lecture. Conservative force is a force with the property that the total work done in moving a particle between 2 points is independent of the path taken. Equivalently, if a particle travels in a closed loop, then the total work done by a conservative force is 0. So, let us study non-conservative force. A non-conservative force is one for which work depends on the path taken and is independent on the position of the points. Friction is a good example of a non-conservative force. Means, a force is called a non-conservative if work done by the force depends on the path taken by a particle between its initial and final positions. Or another definition of non-conservative force is work done by the force over a closed path or during any round-trip journey is non-zero. The force is called a non-conservative force. The work done by a non-conservative force is irreversible. The example of non-conservative force is a frictional force and air resistance force. How frictional force is a non-conservative force? Means we have to show that frictional force is a non-conservative force. Means the total work done by a non-conservative force means frictional force is non-zero or not equal to 0. For that, consider a wooden block having mass m resting on the rough horizontal surface of table. Initially, block is at a position A. Block is moved horizontally towards right to point B through a distance S and then returns to its original or initial position A. During the motion of the block, frictional force always acts opposite to the direction of motion of the block. Figure shows motion of the block on a rough surface. Means with the help of this figure, we can calculate the total work done by a frictional force is non-zero. Initially, the block is at a position A on a horizontal rough surface of table. As it is moved towards right to point B through a distance S. Means S is the distance between the positions A and B. If the motion of the block is towards right, then the force of friction is towards left. Let N is equal to mg be the normal force between the table and the block. Similarly, weight W is equal to mg. Then we consider the position B of a block. The motion of the block is towards left. Then the frictional force is towards right. Again, this is normal force N and weight W, which is equal to mg. So this is a complete figure which shows the motion of the block on a rough surface. So from figure, when block moves towards right, that is from A to B, then frictional force is directed towards left. N is equal to mg, be the normal force between the table and the block. If mu is the coefficient of friction between the block and table, then force of friction is equal to mu mg, where g is acceleration due to gravity, m is mass of the block. During the displacement S of the block, work done by the force of friction is equal to minus mu mgs by applying a basic definition of work done, which is equal to force into displacement. And negative sign shows that frictional force always acts opposite to the direction of motion of the block. Let us consider the first situation, that when block moves towards right, that is from A to B, then force of friction is directed towards left, and the work done by force of friction during the displacement is, suppose, W1, which is equal to minus mu mgs. And in second situation, block moves towards left, that is from B to A. Then the force of friction is directed towards right, and work done by the force of friction during the displacement S is W2, which is equal to again minus mu mgs. So we have to find out total work done. So add these two equations. W1 is equal to minus mu mgs and W2 is equal to minus mu mgs. Hence, the total work done by force of friction in round trip journey is W, which is equal to W1 plus W2. Putting values of W1 and W2, we get W is equal to minus mu mgs minus mu mgs, which is equal to minus 2 mu mgs, where S is the distance between positions A and B. As W is equal to, that is total work done, is equal to minus 2 mu mgs, that is not equal to 0 or non-zero. Hence, the force of friction is a non-conservative force. Next topic is potential energy. In physics, potential energy is the energy held by an object because of its position relative to other objects. It is a stored energy or energy caused by its position. Potential energy is denoted by capital U and its SI unit is joule. It is also defined as the energy possessed by a body by the virtue of its position or configuration. It depends on the height of an object. The higher an object, then more the potential energy. It also depends on the mass of an object. More the mass of an object, then more its potential energy. Its examples are water behind a dam, hammer overhead, food on the plate, a stretched or compressed spring. A person, if he is sitting or standing, there are so many examples of potential energy. We know that energy is the capacity to do work. There are different forms of energy. So mainly, energy is divided into kinetic energy, means energy possessed by an object due to its motion. It's called kinetic energy. Similarly, potential energy is the energy possessed by an object due to its position. Again, there are different forms of potential energy. First is gravitational potential energy, then elastic potential energy, chemical potential energy, and electrostatic potential energy. Let us see one by one. Gravitational potential energy. It is the energy stored in an object due to its position above the Earth's surface, or energy possessed by a body due to its position above the surface of Earth. Mathematically, gravitational potential energy, that is EP, is equal to mgh, where m is mass of a body, g is acceleration due to gravity, h is height. For example, a book on table before it falls. River water at the top of a fall and a child at the top of a slide. Figure shows gravitational potential energy. Then elastic potential energy. It is the energy stored due to deformation of an elastic object. Mathematically, elastic potential energy, that is EE, is equal to 1/2 kx square, where k is spring constant and x is extension. Figure shows the position of unstretched spring, where potential energy is equal to 0, and stretched spring, where potential energy is 1/2 kx square. In the examples of elastic potential energy, a coiled spring, a stretched rubber band, etc. Then chemical potential energy. It is the energy released during a chemical reaction or a change. The energy stored in the chemical bonds of a substance and ready to react with another substance. And the examples are batteries and photosynthesis. And we know that photosynthesis is a process used by plants to convert light energy into chemical energy. Figure shows example of chemical potential energy means battery and photosynthesis. Then electrostatic potential energy. As we know that two electric charges separated by certain distance, they exert a electrostatic force on each other. A system of two electric charges have a potential energy called as electrostatic potential energy. If Q1 and Q2 be the two charges which are separated by a distance r, then electrostatic potential energy is equal to K times Q1 Q2 by R, where K is called Coulomb constant having value 9 into 10 raised to 9 Newton meter square per Coulomb square. Q1 and Q2 be the charge on each object. R is distance between the charge. Capacitor stores electrostatic potential energy. If these two electric charges are alike, then the force is repulsive, and if two electric charges are unlike, then the force is attractive in nature. The potential energy may be positive if the two charges are of the same types, and it is negative if the two charges are of opposite types. We have to ask a question: which object has more potential energy? Objects are given here. Object A is stone and object B is feather. So out of these two, which object has more potential energy? And the answer is object A, that is stone has more potential energy, because we know that stone has more mass than the feather, hence it has more potential energy. Means changing an object's mass can change its potential energy. And another question is, if you drop a ball from the top of these two things, where will be the most potential energy? Two things are A and B. We also know that potential energy depends on height of an object. More the height, then more its potential energy. So the answer is B, because height of tower is more than height of stool. Because answer is B. Why? Because higher the object or more the height, more the potential energy. Or changing an object's height can change its potential energy. Thank you.